This is lecture 2, part 1 of the Foundations of Machine Learning, the course taught by Professor Mohri at Courant. This course topic is learning with finite hypothesis sets. Remember, hypothesis sets are just hypotheses, it's just a function which takes my sample as an input and returns a label or a number as an output. So finite hypothesis set means that I only have a finite number of hypotheses. And how then will we learn in such a scenario? So some computational learning questions like what can be learned efficiently? What is inherently hard to learn? And is there a general model to learning? So computational complexity could be time and space. Sample complexity could be the amount of training data that you need to learn successfully. And mistakes are the number of mistakes an algorithm is allowed to make before learning successfully. Like all of these could be notions of complexity in a machine learning scenario. Yes. So this is part 1 about the PAC model. PAC model means, well, we'll get to it. So definitions and notation for this. X is set of all possible instances or examples. Set of all men and women characterized by their height and weight, essentially. X is just a set of all instances. C, small c, is a concept, it's a function actually, which takes an input from X and gives a label 0, 1. Here we are only dealing with, let's say, 0, 1 classification. So the target concept is something that we want to learn. It's the actual truth, the real truth that we do not know. And to identify this target concept, what we really need to know is only its support. That is, all the values of x's in the set of all possible instances for which the c of x is 1, basically. Because it only goes to 0 and 1, if I give you the set for which c of x is 1, by definition, all the other x's are when c of x is 0. So you only need to know where this function is 1, otherwise it's 0. So we just need the support. C is just a function. It's the target concept that we need to learn. Capital C then is a concept class, a set of all target concepts, So the D then, capital D, is the target distribution, a fixed probability distribution over X. So remember, it has to be a fixed probability distribution, and training and test examples are drawn according to capital D. Capital S is a training sample, some sample. Capital H is the concept hypotheses. Okay, just all the hypotheses that we can formalize, I guess. And the set of all the example is the set of all linear classifiers, whatever. So the learning algorithm then receives a sample capital S and selects a hypothesis H of S, H sub S, because it depends on the sample S, from the hypothesis class, and the goal is that it approximates the real target small c concept as good as possible, and we'll define what good means here. So true error, the real true error or generalization error of the hypothesis H with respect to the target concept C and the distribution capital D is, because it's only a binary classification problem, we only need to look at values where they are same or they're different, either both 0 or both 1, or they are 0 and 1, like different. So the only time our hypotheses are small h, the hypothesis outputted by the algorithm makes an error, is when it is not equal to the value of the real concept, like the real thing. So probability that if I draw any x from this distribution capital D, h of x will not be equal to the c of x, which is the real value, is actually the error that I'm making. And this is the expectation of the 0-1 error, that h of x is not equal to c of x. Basically, it's the expectation of the indicator variable when they are different, and that is equal to the probability that they are different. So that's the risk of hypotheses. Empirical error, because we don't really know what the distribution D is and the concept C is. Empirical error is something that we cannot really calculate the true error. What we can hope to calculate is the empirical error, which is the average error of H on the training sample S drawn according to distribution D. So we still assume that the distribution is fixed. Sample is drawn from the distribution D. We have the H, and we also have C of X, because that is the labels which were given to us by the training, training problem. So what we can actually do is just take an average of all the m points in our sample where hypothesis h of xi is not equal to c of xi. That's literally it. It's just the empirical average. And now from the linearity of expectation, we can say that the expectation over all samples basically of size m from this distribution, the expectation of the empirical risk is the real true risk. And again, we don't really know d, so we cannot really calculate this, but this is something to keep in mind, that this quantity r hat, the empirical risk in expectation, is equal to the real risk. And we studied probability bounds in the last lecture, so somehow maybe we can calculate the empirical risk and give some high probability bounds on what the true risk of this hypothesis could be, and we'll see that. So now the PAC model. The PAC learning model is the probably approximately correct model. So the definition is a concept class C is PAC learnable if there exists an algorithm L such that, okay, a concept class C, capital C. So concept class is a set where there are all possible concepts that you could ever want to learn, you know. This concept class C is PAC learnable if there exists a learning algorithm L such that for all, now here's something, I fix a concept class C, and for all small c concepts in that concept class C and a small number epsilon and a small number delta and all distributions d over the sample, like of the sample, the probability that the risk of hypotheses is less than epsilon is greater than 1 minus delta. If this were to be, if this was the condition that were to be enforced, then what we need is that sample S of size m should be polynomial in 1 over epsilon and 1 over delta for some fixed polynomial. All right, let's look at this, what this statement says. This concept class C is PAC learnable if there is an algorithm L which takes a sample and a concept class that we need to learn, and now this holds for every concept in that concept class. So I gave you a sample and there is a concept which is hidden from you. If the algorithm returns an hypothesis which has a small risk with a high probability, so epsilon is a small number, delta is a small number, so 1 minus delta is a large number, let's say delta was 0.01, so this is like probability greater than 99%, like more than 99% sure, you're sure with more than 99% that the risk is less than 5%, let's say. So now this algorithm gives me a hypothesis which has a small risk with very high probability if my sample size is polynomial in 1 over epsilon and 1 over delta, and there is a fixed polynomial. So now it makes sense, like, if my epsilon were to decrease, that you want to make it more and more accurate, your m starts to increase, that you need more and more samples. If your delta start to decrease, that you want even more and more higher probability, that I am 100% sure that my risk is less than 5%, you need to give more and more samples to the algorithm. That's basically an intuitive way to think about it. So this essentially is saying that the sample size is polynomial in these two parameters that as a user we define. Let's say epsilon is 5% and delta is 1%, whatever. So it has to be polynomial in these two things. And if my sample size was polynomial, then if you give me any concept in that concept class, I will be able to return an hypothesis which has a small error with high probability. And now if this holds for every concept in that concept class, I can say that this concept class is PAC learnable. All right. So this essentially saying that a concept class, basically, things that I'm actually interested in learning, is PAC learnable if I have a polynomial dependency on the accuracy and the confidence parameters. So concept class C is known to the algorithm, right? And this is a distribution free model. The concept class C is known to the algorithm and this is a distribution free model. That means we did not make any assumption on D. However, both training and test samples are drawn on D. We have the probably confidence is greater than 1 minus delta and approximately correct. That is, accuracy is greater than 1 minus epsilon. So this part is the probability, and this part is the approximately correct. So probably, approximately correct. With high probability, it is approximately as correct as it gets. Essentially, that's why it's called the PAC-learnable. So an efficient PAC learning algorithm would also run in polynomial time in 1 over epsilon 1 over delta, And now there is another extension to this. What about the cost of the representation of the concept class? So you have the concept class, but you need to represent every concept in that concept class, right? Like you need to store it somehow, right? Like you need to represent it. So what is the cost of representation? So another like new definition is, let's say the cost of the sample, each sample is order n, and the cost of the concept C is order size of C. Then the extension is that the running time is not only polynomial in 1 over epsilon 1 over delta, but it's also polynomial in the cost of the sample, cost of the storing of the sample, and the cost of the hypothesis set. Essentially, this is whatever. This is okay, fine, okay, I agree, fine. The real thing is this thing. Basically, this entire slide, what it says is, if you want a more accurate and more like higher probability, you need to throw in more samples. Okay, that's fair. That's the intuition. But this is saying that, okay, if my samples are polynomial, then I have a good I have a PAC-learnable algorithm. That's what they're saying. If my sample size is polynomial, it could be exponential, If there is some algorithm which requires an exponentially higher number of samples, it is not PAC-learnable. This definition is simply what PAC-learnable means. So if you give me a sample size which is polynomial in 1 over epsilon and 1 over delta, then this concept class C is PAC-learnable if my algorithm can return a hypothesis which has this particular guarantee that the errors are low with high probability. That means that concept class C is PAC-learnable. Now let's get to an example of this, So learn an unknown axis aligned rectangle using a small labeled data. So what you have is basically just forget the two rectangles. What you have is dots on the 2D plane, and what you have is their labels. Let's say blue is +1 and red is 0. So what you need to now give me is an axis aligned rectangle, basically like axis aligned rectangle, which is basically, that's the concept class, all axis aligned rectangles. And now I need to know if it's PAC-learnable or not. So our hypothesis is a rectangle R prime, right? And in this case you can see that R prime is, there are some false positives, like R prime will give this as +1, R prime gives these two as +1, which is right, but R prime gives these as -1, which is wrong, right? So it comes back to that idea that you can identify a concept with its support. So the support is just the points which are inside this rectangle. So simple method then is to choose the tightest consistent rectangle R prime for a large enough sample. So this is the class, this is the hypothesis class, this is the concept class, axis aligned rectangle, and this is my algorithm. That what I'll do is I'll look at all the points, and because I know that the concept is because I know that the truth is a axis aligned rectangle where the inner points are +1 and outer points are 0, what I will actually do is go to the sample and give me the tightest fitting rectangle, such as this one, for this particular number of samples. Now the question is this PAC-learnable? So if I want to increase my accuracy to 1 minus epsilon, how many samples do I need? Basically, are they polynomial or are they something else? That's the question. So what is the probability that the risk of this R prime is greater than epsilon? We'll answer that question. So let's say you fix an epsilon and assume that the probability of that region is greater than epsilon. Otherwise it's trivial, because if the entire thing is so small, that it's the entire thing, the measure of the area of this rectangle itself is less than epsilon, then that doesn't matter, because you'll always be greater than epsilon, sure, right? That's like saying that if you have a sample which has 99% positive labels, then all you need to do is just output positive and you'll always be correct like 99% of the time. So assume that the the real rectangle that we want to learn, basically the blue one, R, has an area which is greater than epsilon. So now let R1, R2, R3, R4 be four smallest rectangles along the sides of R, such that the probability of this region is greater than epsilon by 4. So probability of R1 is greater than epsilon by 4. This is the smallest possible rectangle for which the probability is greater than epsilon by 4. In continuous, the only reason we write it this, in this way, that this is the smallest rectangle for which the probability is greater than epsilon by 4, is because it need not be continuous, right? The distribution need not be continuous. It could have jumps or whatever. But if it were, let's say, a smooth continuous distribution, then probability of this region will be epsilon by 4, because the smallest is essentially the one which gives you epsilon by 4, whatever. Anyway, so the rectangle R goes from left to right and bottom to top, right? So R4 goes from left to S4 and bottom to top. And what is S4? S4 is the infimum of all the S's, such that the probability from L to S and B to T is greater than epsilon by 4. Fine. And the probability if I remove S4, like remove this particular line, is less than epsilon by 4. Fine. This is essentially saying that the probability of this region is epsilon by 4, probability of this region is epsilon by 4, probability of this region is epsilon by 4, and probability of this region is epsilon by 4. I'm not saying that their combined probability is epsilon because you have overlaps or whatever. I'm just saying that this particular bar, this one, has epsilon by 4, and with the overlapping R1, that has probability epsilon by 4, area epsilon by 4, if you will. So if I give you a tight rectangle R prime, the errors can only occur in regions which are outside of R prime, I'm sorry, but inside R. Because what happens is everything which is outside R is also outside R prime, because R prime is inside R. So whatever is outside R is of label 0, and R prime will also give it as label 0. Whatever is inside R prime will give it as label 1, but R also gives it a label 1. But something which lies in this particular region, let's say, R prime will give that as a label 0, but R will give that as a label 1. So errors can only occur in the regions which are outside of R prime, but inside R. So now, what is the probability? What is the probability that what is the risk of this? What is the probability that the risk of R prime is greater than epsilon? The probability that the risk of R prime is greater than epsilon is that, it can only happen that the probability of R prime is greater than epsilon if R prime misses at least one region. Because if R prime did not miss any region, then the sum of the regions are epsilon by 4, less than epsilon by 4 in fact. So the risk of R, the area which is outside R prime is less than epsilon by 4. Like, if imagine, because I chose my regions as such that their areas are epsilon by 4, if R prime were to be meeting all of these regions, R1, R2, R3, R4, it is strictly inside them, and by being strictly inside, it means the area which is covered just by that one is strictly less than epsilon by 4. So even if I give you the leeway of counting every area, every region as a disjoint one, the error would be still less than epsilon if it were to meet all the regions. So the probability, the only way that the risk of R prime can be greater than epsilon if R prime misses at least one region Ri, right? So the probability that the risk of R prime is greater than epsilon is that probability that R prime misses Ri, or R prime misses R1 or R2 or R3 or R4, which is basically the union. Like, it misses at least one region. And by using the union bound, we can say that this probability is less than the sum of all of these probabilities. Like it missing every area, every region individually. And the probability that R prime misses Ri is that there are no points in R1. There were no points in R2. Like if you sample m points, none of them landed up in R1 or R2 or R3 and R4. And what is the probability of that happening? The probability of that happening is 1 minus epsilon by 4 to the power m. And for all 4 regions, so it's multiplied by 4 basically. If you think about it, like though you sampled m points and none of them landed in this probability region R1, which has the probability epsilon by 4. Well, how is that possible? That is only possible for 1 minus epsilon by 4 to the m. And doing this for all 4 regions. I know this is like way over counting, but we are still trying to give just an upper bound. So the probability that the risk is greater than epsilon is less than 4 times 1 minus epsilon over 4 to the m, which is less than 4 e to the minus m epsilon by 4. Just using the fact that 1 minus x to the power m is less than e to the x. E to the x and whatever, like something. 1 minus x is less than e to the x. Yeah, 1 minus x is less than e to the minus x. My fault. Yes. Oh, this is an identity. Fine. Just believe me. The key idea is that we used geometry here. The fact that it misses, the fact that it could have a error of more than epsilon can only be possible if it misses at least one region. Because if it were not to miss any regions, then it cannot have a probability greater than epsilon by epsilon. Because individually, all of these regions are epsilon by 4 probability, and if you met all of them, then your error is definitely less than epsilon by 4. So the probability that this is greater than epsilon is less than 4 this exponential this whatever. So now if I set this side equal to delta, what we have is that m, the number of samples, has to be greater than 4 over epsilon log 4 over delta. Right? All I did was look at this probability that risk is greater than epsilon is less than some number. And for PAC learning model, we need to get it in the form that probability risk is less than something is greater than 1 minus delta. So this is of the same form essentially. I could just do 1 minus probability this and 1 minus probability and take the probability to that side. So what we'll get, that probability risk is less than epsilon is greater than 1 minus this number, which is delta. So I set this as delta. And what I get is that the number of samples m then should be greater than 4 over epsilon log 4 over delta. Then for m which is greater than 4 over epsilon log 4 over delta, with probability at least 1 minus delta, we have that the risk of this r prime is less than epsilon. Boom. So it is PAC-learnable because it's polynomial in 1 over epsilon and it's let's say even better than polynomial in 1 over delta. So it's an infinite hypothesis set, but it's a simple proof. And the only reason it's so simple is because that we use geometric properties. So does this proof readily apply to other similar concept classes? Not really. For example, non-concentric circles, it just does not apply because you cannot really capture the areas or whatever. So the next video, this one has been a little bit complicated. So let's go back. And the key idea is that the intuition is you need more samples to be more accurate with higher confidence. Boom. Okay, fine. But how many more samples? How is that sample? How many more samples and how would you quantify it? If it is polynomially given by the parameters, then you have a PAC-learnable class, basically. And this class then, axis aligned rectangles, is PAC-learnable.